The waves in two dimensions. Before we start, let's not forget that all the concepts, equations, quantities, terms, phenomena that happen to waves that we studied in one dimension, they apply to waves in two dimensions. All right, we're just trying to put the analogy between the two of them. So here is how a wave in 2D would look like. Um, if this is the source and it's transmitting some waves, think of a ripple tank, of a faucet dripping into water surface. And these are the ripples that they spread out, they look like concentric circles, okay? To relate it to a one-dimensional wave, what I did here is let's pretend that this is the top view, and then underneath here I put the side view. So what I did, I drew dashed lines matching those concentric circles. These concentric circles, by the way, we call them front waves or wave front, whichever term you come upon. A front wave pretty much is a crest on a one-dimensional wave. So now that we know that, here is the source, and here's what's happening. So this is the source, which is transmitting, and then here we're going to have a crest, and somewhere in between we'll have somewhere in between we'll have a trough, right? So it's like this, and then like that, and then like this, and then like that, and so on and so forth. So this is what this wave would look like in two dimensions. All right. So which means between these front waves, there's going to be, which are crests, are going to be troughs, right? So if I draw this dashed line between each of these circles, that's a trough, okay, where the wave is all the way at the bottom, okay? And I can continue and do that for all of them, but we understand the point here. Now, what do you think the distance between two wave fronts or front waves would be? And if you thought about it right now and you wanted to say it, you are correct. That is a wavelength, okay? So the distance between two front waves is actually the wavelength, okay? Obviously, the distance between a crest and a trough, it's half a wavelength, all right? So that's something that we want to remember. So based on this frame of work, Huygens, and based on experiments, Huygens came, a scientist, the father of the wave nature of light, came up with a principle known as Huygens' principle that every point in a front wave or wave front will serve as a source of the same type of wave. Now, what does this mean? If I go back to this diagram, every point here, every little point, as many as you think of, will actually be a source of the same type of wave, all right? And what happened is all of them together will kind of be put like in an envelope by the next front wave. How do we observe this? So that's his principle, okay? Huygens' principle, every point in a front wave will serve as a source of the same type of wave. How do we observe this in an experiment? If we were to place an obstacle, an opening, so let's say this is water, sorry, and then we put a wall, and we allow only one point of this wave to go through, right? So this is like a box. So what's going to happen around here, we're going to have a lot of reflection, bouncing. We're not interested in them right now. But what's going to happen on this opening Actually, let's not put it here. There is an opening here. This opening, you will notice waves or wavelets, as they are called, to come out of here, and they will be exactly the same as the waves inside the box. All right, so will be, this is the original source, right, and this is the opening. Okay, will be the same type of waves. All right, so this is an experiment that demonstrates how Huygens principle for any waves happens to be true. So what Huygens was saying that this is true also for light. Okay, so light is behaving like this, like a wave, and every point of the front wave of a light wave will serve as a source. All right, and that's what made um, uh, um, Young thinking about his own experiment, right? Because if we had, let's say that we have two openings, right? So we have a source, and we have, so here's a source, okay? And instead of one, we'll put a wall that has two openings. So let's put it here. All right, so it has one opening here and one opening down here. Okay, they are a distance d from each other, these two slits, as we want to call them. Okay, so let's say that we have some front waves that eventually reach this point. Okay, so which means if a front wave has reached this point, on that point, on the other side of the wall, there will be two sources now, all right, that are transmitting on this space. So now this is source number one, this is source number two, this is the original. Source number one, source number two, and the original are all coherent sources. All right, for the obvious reason based on Huygens principle. So what's going to happen to these waves as they continue to propagate? They will eventually interfere with each other. So we should be able to see some sort of an interference pattern. All right. Let's look into that interference pattern. So we're okay so far. So again, what we talked about was what does a wave look like in 2D, a wave motion, uh, front waves or wavefront, what is the distance between them, what is between them, the trough, okay, Huygens principle that every point in front wave will serve as a source of the same type of wave, that is for sound, water, you name it, as long as it is a wave, this is true. So it should be true also for light. And I said, what happens if we have, how do we observe this? If we have an opening, as soon as the wave hits that just opening, the wave will continue to propagate on the other side. Of course, not the same intensity, all right, not the same amplitude anymore. And we understand why, because remember that wave is a transfer of energy. So some of the, only a portion of this energy will go through, okay? So the wave will have a much lower amplitude on that side. However, will be exactly the same in terms of behavior as the original source, right? And we said, well, what if happen if we have two openings? Then we'll have two sources emitting the same wave, okay, so coherent sources as the original one, albeit with a smaller amplitude, and then we'll have a condition for some interference, all right? So of course, we've seen this earlier in physics. However, now perhaps it's time to do some math behind it to see what is a relationship between all the components in here, all right? So here is a better diagram of two sources. So I have two coherent sources, S1 and S2, and the distance between them, actually let's do it on the other side. Let's get back some of those circles. All right. So what we have here, we have some distance between the two sources. Let's call that D. All right. So the sources can get closer together, further apart, and whatnot. We also have the wavelength, which is since they are coherent. Remember, these are coherent sources. All right. So the wavelength, the frequencies, so lambdas, frequencies, and they are traveling through the same space. So the speed of the wave is all the same. And we have this distance between the sources. All right. Now you notice that there are some points here, like this one here, this one here, this one here. And if we continue, they all have crest plus crest, right? So where else do we have them? Well, we have them here. Okay, we have them here, and so on and so forth here. All right, and here. Okay, what we expect to happen exactly halfway through. So if I draw this line like this, like such, as you can see on all this line, we have always a crest and a crest meeting together, right? We also have on this line here. So let me first put all the dots here where we expect to have this constructive interference, okay? So all this, so I'm going to put a legend, we have constructive interference, all right? Now, where does the destructive interference happens? The destructive interference will happen when, remember, a crest and a trough will meet each other. Remember, it have to be out of phase. Two waves out of phase will actually cause a destructive interference on that region. So let's put them with red. So before I do that, let's draw some troughs in here. So here are a few, just so that we get an idea. And here are the one from the other side. All right. And now remember, it has to be wherever a dashed line meets a solid line, we'll have a destructive interference. So for example, we'll have one here, we'll have here, we'll have also here, and the same on the other side. We'll have one here, here, and there, and here. Okay. However, if a trough, let's put on a legend here, so the red dots are distracted, or as you call them, nodes, distracted interference. Okay, so interference. Okay, you can see that all the constructive interference are happening along some lines that go like this, right? And they will obey to some very clear math, so kind of like they spread out, okay? Destructive interferences will happen along wherever we have the red ones, all right? So of course my diagram is not that, but as you can see, the destructive interferences and the constructive interferences kind of like so along all these red lines, we'll see destructive interference, which means we won't see neither a crest nor a trough. And on the orange lines, we will see constructive interference. So we'll see super crests or super troughs. Okay. So what happens if I place, let's say, a screen, okay, or some sort of a screen where we can see this, right? Let's say that we're the observer on this side. So all these points will be an alternating of constructive and destructive interference. All right, let's take one arbitrary point right here. All right, so this is a point P, and let's say that we have here a destructive interference. Okay, so it's a point that has a destructive interference on that horizontal line there. Let's see what the relationship is between all the um, quantities that we have at hand here. Okay, so this is R1, that's the path of the first source, and the other one is R2, is the path of the second source. So what I'm going to do now, I'm going to take that diagram as a triangle and put it up here. By the way, you'll notice that in the middle, on that solid orange line, we're always going to have a constructive interference. Remember, the two sources are coherent after all. All right, so here is, let's start with destructive. Remember, whatever math we're doing here applies to all the waves. If a certain phenomena behaves like a wave, whatever we're coming up here with, this will apply to that phenomena as well. All right, so it could be sound again, could be water, could be light, all of them. So here are the two sources. This is a distance d between them. And this point P here is where we got some destructive interference. All right. So let's say this is not the first one, not the second, third, fourth, fifth. This is the nth node. All right. We don't know which one is the nth one. So you notice here that the R1, it's much shorter than R2, right? So how much shorter is that? It's multiples of half wavelength, as you remember. Okay, so this is R1, this is S1, this is R2, this is S2, and here remember we have destructive interference. All right. So what we have here from the middle, usually this is a midpoint. So let's write D here. This is midpoint. We measure usually an angle. All right, the angle with respect to that right bisector. Okay, remember that middle line, the orange line. Actually, let me draw it orange, where we had all the constructive interferences always, right? So that's how we measure things. So this is some angle. This is some angle theta. Okay. So what we have here, and remember this point P is really far. So let's start with destructive, right? So we have R2 minus R1, which is delta R, right? So delta R is a multiple, odd multiple of half wavelength, right? Now let's see on the diagram, what is that delta R? And we can do that by drawing a little, by doing some trigonometry tricks here. All right. So we have this line. Sorry, let me just do it again. And so we have this line, which is perpendicular to the other path. So remember, P, the condition here is P is really far. All right, so now we'll see what relationship we'll have between the difference in path, the D, and the angle. So we're trying to find again the difference in path with respect to the distance between the two sources. So we are going to use, and remember, this is an approximation that we use for a point P that is really far from the two sources. So if we do that, then delta R is actually just this side here, right? The difference between R2 and R1. And if you can look at that shaded triangle, delta R is actually D times sine theta, right? Because if this is theta, then this is theta as well. Remember, we constructed that dashed line so that it's perpendicular to the second path, starting from the first source. All right. So what we find is that this d sine theta, which is a difference in path, is actually for destructive interference at a given point. Here P is like that, okay, is some odd multiples of half lambda, where lambda is the wavelength of the waves that are being transmitted by the two sources. Of course, we need to know also the location of this point P. So we are very interested in this distance from that right bisector, if you will, and we call it xm. Okay, so the distance of the mth node, if you will, from the center. All right, and if you notice that we have a another triangle there that we are going to use, and that is this triangle here. All right, and we can figure out what is the relationship between xm. The distance, by the way, the vertical distance of the point P from the plane where the sources are is d. So which means this orange line here also is d meters or centimeters of unit of measurements long. Okay. Another thing that so what we have there, we have and for in general we have tan theta, right? So we have tan theta. If you look at now this triangle here, the big one, tan theta is equal to xm over d. Remember, d is the distance between the sources and the point P, the vertical distance, okay? So these are the two relationships that you would use to figure out all those for any type of sources, no matter how far they are from each other. However, if if theta is less than, let's say, actually less than 15 degrees, but let's say less than 30, all right, then sine theta is very close to tan theta, all right. Again, remember, these are very valid equations that we can use. We're just going to a further approximation. We're saying, let's see if the angle is very small. What does it mean? It means this distance d is a lot greater than the distance d between the two sources. In that case, we have the following. We have, again, d sine theta is equal to 2m plus 1 times lambda over 2. And then we have also sine theta is approximately that distance of the point that we're interested in over the distance of the from the plane of the sources. All right. So if we combine these two equations, then we get d xm over d is equal to 2m plus 1 times lambda over 2. So this is the condition for destructive interference. And we don't have to do the same math again, but for constructive interference, remember constructive, the condition for constructive interference was that the difference in path should be some multiples of lambda. All right, let's recall that and have that in mind. We write the same condition. So d times xm over d is equal to lambda times m, where m is known as, so m is 0, 1, 2, 3, and so on, is also known as the order. All right. So we have the maxima or minima, or the destructive and constructive interference of the first order, second order, or the central one. Okay. So in general, for any waves, so again, let's draw a little diagram here now. So we have two sources, so we can better visualize it. There are distance d between them. Okay, and then we have a screen here. Whatever that screen is, some sort of a sensor, right? That's what I mean by a screen. And then the distance between the screen and the sources is d. Then we have a what we have a series of a combination of minimas or constructive or antinodes, and destructive. Sorry, this is also constructive. I meant this one because they alternate, destructive or node. All right. They are also known as maximus. These are known as minimum. This is the central one. Okay, the one right in the middle. And then at any point, this is the mth. So, for example, 0, 1, 2. Okay, so this is 1, this is 2. But in general, the mth, that this is these are the constructive, the nodes, the maximus, and then you have the destructive antinodes. So these are given. What else was given again? The wavelength, right? What we have is that to rewrite the distance here from the center, it's called xm. Okay, so how far from the center? Okay, the angle is theta m. Okay, so in general, we figured out the following relation. This is the approximation. So these d sine theta for constructive or maximus. All right, we have d sine theta m is equal to m times lambda, right? For destructive, we have d sine theta m equal to 2m plus 1/2 of lambda over 2. All right. Then we had the approximation. So if d is a lot less than d, then we have this equation here for constructive. We have dxm over d, right, is equal to lambda m lambda. All right, and for destructive, we have dxm over d equal to 2m plus 1 lambda over 2. Remember what m is, right? The order, which one, how far away you're going from that central line. So these are the equations for the conditions to find the location, exact location, and this is to find the directions for constructive and destructive interference for minimum and maximums. Okay, and m again is the order, first, second, third, starting from the center. So m is 0 for the center, 1, 2, 3. So the greater the m is, the further to the right or to the left you're going from the center. All right. One more thing here. What is delta x, right? So delta x is the distance between adjacent antinodes, for example, and the nodes will be the same, by the way. All right, so if I were to find that, I'll do the following. So delta x is, for example, x m plus 1 minus x m. All right, so I'm going to use this equation here, the dxm over d equal to m lambda, to solve it, right? So we have d over d times m lambda times m plus 1 minus d over d times lambda m. And if you are going to factor some common factors here, you have d over d times lambda. All right. So what this delta x again is the distance between adjacent nodes and whatnot. As you can see, between adjacent nodes or antinodes. As you can see, delta x depends on d, depends on lambda, and depends on the distance, okay? So this could be a good example of examining what would happen to a pattern at a screen if you change the distance between the two sources, okay? So if you decrease the d, the little d, then guess what? Delta x will decrease as well. If you use a source with a bigger wavelength, the delta x will increase. If you go further away from if you place a screen really far from the sources, then delta x will decrease again, okay? So that could be a good dependency to be asked on questions in a conceptual test or things like that. So to recap, we talked about waves in 2D in general, the Huygens principle. So the waves in 2D, the Huygens principle, how it's shown in experiments, then extra thinking, how can I get to coherent sources with the two slits, all right? And then we went into, well, what happened when you get an interference. So first we just showed what would happen in general if we have two sources. We talked about coherent sources. The two sources are at distance d. And then we said, well, let's find the conditions to have a destructive interference of the mth node. Sorry, this is m actually. At the point P somewhere in some sort of a screen, right? That black line. And we went through all the math. And to cut it short, we got to these equations that d sine theta is 2m plus 1 times lambda over 2 for destructive interference. All right. And that distance of the point P from the central line or from the central maximum is related with this tan theta equal to xm over d. However, for small angles, we can make that approximation that tan and sine theta are almost the same. So we got to these relationships in general for constructive and destructive interference, and then we described it on a little diagram. What does everything mean? And then we put both equations, and that we had a conversation about what happened to the distance between adjacent antinodes or nodes for that matter. And we saw that it depends only on the distance between the sources, the distance between the source and the screen, and the wavelength. Okay, so now it's time to talk about the double, which is exactly this, by the way, but the double slit experiment that showed once and forever that light is also a wave.